Ever notice how your phone's battery, like, seems to last longer, even though it can do way more than those, ugh, clunky laptops from even just a few years ago?
It's really quite remarkable.
It's the magic of shrinking transistors,
Yeah,
right?
it is. Yeah, shrinking transistors and these surprising, well, maybe not so surprising, but really interesting laws that govern them.
And that's what we're diving deep into today.
Yeah, the fascinating world of transistors.
Specifically, MOSFETs, right?
Yes, MOSFETs.
To uncover how they work and why their size matters so much.
And it's not just how they work now, it's, how they've evolved.
Right, like how did we get from those, I don't even know what to call them, from back in the day?
Room-sized behemoths to microscopic marvels, really.
And those impact everything, right?
Yeah, from your smartphone to, well, space exploration, really anything you can think of.
Yeah, and why understanding their journey helps us even, like, peep into the future of tech.
It all starts with kind of the heart of these devices.
The MOSFET.
The MOSFET, exactly.
Okay, so before we, like, shrink anything.
Yeah, let's break it down.
Let's break down what a MOSFET actually is.
So imagine a tiny gate.
Okay.
And this gate, it's like a drawbridge.
Okay.
And this drawbridge is controlling the flow of electrons between 2 points.
Got it.
And these points are called the source and the drain.
Source, drain.
And this flow, we call that current.
Current.
The lifeblood of all things digital, really.
So, like, the gate is like the control booth and the electrons are the cars.
Yeah, you got it. You're getting it. Applying voltage to the gate, it's like lowering the drawbridge.
Right.
Right?
Yeah.
So it creates an electric field. And that lets the electrons, our cars, flow from the source to the drain.
Okay.
No voltage, no flow. Just like an open drawbridge would stop traffic.
Makes sense.
And by controlling this flow, we're basically controlling the ones and zeros that make up our entire digital world.
Wow, that is pretty impressive for something so tiny.
Yes, it is.
But they weren't always so small, right?
No, not at all.
Like, how big were we talking?
Oh, in the early days,
Yeah.
these transistors were much larger. It's one reason why computers used to take up entire rooms.
That's wild. Okay, so how did we go from room-sized computers to something that, like, fits in our pockets?
Well, that's where this incredible shrinking transistor comes in, and it's driven by something you've probably heard of, Moore's Law.
Moore's Law, yeah, vaguely.
So back in the 1960s, Gordon Moore, he observed that the number of transistors on a chip, it was doubling roughly every 2 years.
Wait, every 2 years, double the transistors on the same size chip? Okay, first of all, how are they even making them smaller, let alone, like, cramming more in? How is that even possible?
That's where the ingenuity of engineers comes in.
Yeah.
And the concept that made it all work, we call it Dennard scaling.
Dennard scaling. And this is how they managed to shrink those transistors without, things overheating or needing a power plant to run them.
Exactly, exactly.
Yeah.
Dennard scaling basically meant that as transistors shrunk, their power densities stayed the same.
So, like, if you shrunk a car but kept the horsepower the same?
You got it. Yeah. That's Dennard scaling in action.
That's incredible. So not only were things getting smaller, they were becoming more efficient at the same time.
Exactly.
No wonder it seemed like technology was, like, accelerating so rapidly. So it sounds like we had it pretty good for a while, right?
We did, yeah, for a while.
Things getting smaller and faster and more efficient all at the same time.
Mm-hmm.
But you said Dennard scaling hit a wall.
Yeah, it did.
What happened?
Whoa.
Could we just, like, run out of space to shrink?
Kind of, yeah. You can only shrink things down so much before, well, the laws of physics start to fight back.
Okay, yeah, that makes sense.
Yeah.
I guess at some point you hit, like, a fundamental limit. But, like, what are these roadblocks? What's actually happening at that tiny scale?
All right, so imagine those tiny drawbridges again.
Okay, the gate.
Yeah, right. As they get smaller and smaller, the paths for the electrons, they get narrower too.
Okay.
And just like with real traffic, things start to get, well, a little congested.
Oh, so all those electrons, like, crammed into a tiny space, that generates more heat. Like a traffic jam on a hot day.
Yes, exactly. And just like your computer fan, when it's going on overdrive,
Yeah.
managing all that heat
Yeah.
becomes a major, major challenge.
So smaller means hotter.
Unfortunately, yeah.
And that obviously causes problems.
Mm-hmm.
But what else went wrong? It can't just be heat, right?
Right. So to keep these minuscule transistors from, basically frying themselves with all that heat,
Yeah.
we also had to lower the voltage that was cowering them.
Yeah, that makes sense. Lower the voltage, lower the heat. You wouldn't want to overload those tiny circuits.
Exactly, yeah. But lowering the voltage, it brought a whole other set of issues with it.
Okay, so what happened? What's wrong with lower voltage?
Well, think about trying to have a conversation in, like, a really noisy room, right?
Okay, yeah.
The quieter you speak, the harder it is to be heard over all that background noise.
Right, right. So in a transistor, the noise is causing the problem. What is that noise, though?
We call it leakage current. Remember how the gate acts as that drawbridge, controlling the flow of electrons?
Yeah, open bridge, electrons flow, closed bridge, no flow.
Well, at these incredibly small sizes and with the lower voltages, some of those electrons, they get a little bit sneaky.
Sneaky?
They start tunneling through the gate even when it's supposed to be closed.
Tunneling? Wait, like they've dug a secret passage under the drawbridge or something.
It's kind of like that, yeah. It's a quantum mechanics thing, a whole other deep dive maybe.
Yeah.
But basically, it leads to wasted energy
Yeah.
and even more heat.
Ugh, not what you want.
Not at all, no.
So we've got heat problems, electron smugglers, and, like, on top of that, we have quantum mechanics messing things up.
Pretty much, yeah.
Sounds like Dennard scaling had a rough go in the end.
It did. But it had a good run. You know, it propelled us forward for a long time. But yeah, by the mid-2000s, it was clear that we needed some new innovations if we were going to keep the progress going.
So what happened next? Did we just give up on making things faster and more efficient? So we didn't hit a dead end, right?
No, not a dead end.
Our engineers, they're smarter than that, I hope.
Much smarter.
So what happened?
Well, innovation, it rarely stops at a dead end.
Yeah.
You know, it just finds a detour.
Okay, I like that.
So while Dennard scaling, that might be fading into the sunset.
Okay.
The drive for better, more efficient tech, well, that's still going strong.
So what's the detour?
Well, it's a multi-pronged approach.
Okay.
One way is through new materials.
Okay.
Remember those pesky electron tunnels we talked about?
Yeah, the sneaky little escape artists.
Yeah, those guys. Well, we're now using materials with higher, what we call dielectric constants, high dielectrics, for the gate insulator.
Higher dielectric constant, what does that even mean?
So think of it like this. A higher dielectric constant means the material is better at kind of keeping those electrons in line.
Okay.
Even with a thinner insulator.
Okay.
It's like reinforcing the walls of the tunnel, right?
Got it.
To prevent those escapes.
So thinner insulators, fewer leaks, and we can keep shrinking things.
Well, not exactly shrinking, but definitely improving.
Okay.
These new materials also allow for better performance at lower voltages, which helps with that whole heat problem.
Right.
And speaking of improvements, we've also moved on from those kind of clunky polysilicon gates to more efficient metal gates.
So we're like upgrading the entire infrastructure of those microscopic highways.
There you go. Yeah, that's a great way to put it. But it's not just about materials, though.
Okay.
We're also getting creative with the physical design of transistors.
Okay.
Remember how we talked about things getting too small?
Yeah.
Well, now we're building up.
Building up, like stacking transistors on top of each other.
You're close. Think of it more like skyscrapers.
Okay.
We're using 3D designs now, like FinFETs.
FinFETs, okay.
Where the transistor channel is shaped like a fin.
Okay.
Sticking up from the silicon.
So instead of just making the highway longer, they're making it taller.
Exactly.
Yeah.
This increases the surface area
Okay.
for the electrons to flow.
Got it.
Boosting performance without needing to shrink the transistor itself any further.
That's really cool.
It's a win-win.
Yeah. But all of this still relies on, like, making the individual transistors better.
Right.
Are there ways that, like, we're changing the whole game completely?
Absolutely. Remember how I mentioned like a different law earlier?
Yeah.
That's where Kuhme's law comes into play.
Kuhme's law. Okay.
And it states that the energy efficiency of computers, so the amount of computation you get per joule of energy,
Yeah.
it's been doubling roughly every 1.57 years.
Wow. Okay, so even if we can't make individual transistors, like, drastically better on their own,
Right.
we're finding ways to make them work together more efficiently.
Exactly. And one way we're doing that is by using multi-core processors.
Oh, multi-core. Okay.
So instead of one super fast processor core,
right.
we now have multiple cores all working together.
Of each one.
It's like a specialized worker, in a factory.
So it's like having a team of specialists instead of one overworked employee.
That's a great analogy, yeah.
Mm.
And this division of labor, it allows our devices to, handle more complex tasks while using less energy overall.
Yeah.
Think about like streaming a video on your phone.
Yeah.
It's a really complex task,
Right.
and it benefits from having multiple cores all working in tandem.
That explains why my phone can, like, stream HD videos for hours, while older devices, they struggle to even play a simple MP3.
Exactly.
It's really quite amazing how far we've come.
It really is, yeah. And it's not just about phones either.
No.
These advancements, they're impacting everything. Laptops, data centers, you name it, making them all more powerful and more energy efficient.
So it sounds like even though, we've hit some roadblocks, the future of technology, it's still incredibly exciting.
Absolutely. We are constantly finding innovative solutions to, overcome these limitations.
It really makes you wonder, though, about, like, the long-term implications of all of this.
Right.
If Kumi's law keeps holding true, if things just keep getting more energy efficient.
Yeah. Could we eventually reach a point where our devices are so efficient they practically run on air?
It's possible.
What happens then? Does our understanding of computing fundamentally change?
It's hard to say.
It's pretty mind-boggling to think about.
It really is. We'll just have to wait and see.
Well, on that note, we're going to have to wrap up today's deep dive on the incredible shrinking transistor.
This was fun.
Always a pleasure. Until next time, keep those circuits buzzing.